should start. So, Mr. Matteo Pietraccini, we are here today for the presentation of your PhD, which is intituled "The Mechanism Involved in the Fast Combustion of Organic Powders." So, you are defending your PhD in order to get the title of doctor at the University of Lorraine. I'm going, just before your presentation, I'm going to present a member of the jury. And I'm going to start with Guy Marler of Paris, who is also a reviewer of your manuscript. We have also Dr. Gaël Lecom of the University of Lyon in South Lyon. Agnès Janès, Dr. Agnès Janès, who is from the CRAMIF in Paris. We are waiting for Dr. Luca Marmot. Yeah. We hope that he will be there in a few seconds or minutes. And after, the jury is composed of your supervisor, Professor Olivier Dufaux, and the Dr. Pierre-Alexandre Claude, and Dr. Anthony. OK. On attend un petit peu pour le cas où on va commencer. So we will start, and with your presentation, 45 minutes. Is okay for you? Yeah. Okay. Thank you.
Thank you very much, Mr. President of the jury. It's a real honor for me to be here presenting you the main results of my thesis work entitled "Mechanisms Involved in Fast Combustion of Organic Powders, Application to Dust Explosions." First of all, I would like to introduce the main themes of my work by presenting you some element of general context. Dust explosion, the history of dust explosion begins in Turin, Italy, where the first ever dust explosion was observed and documented, classified as a spontaneous inflammation. Then, with the second industrial revolution, with the increasingly important use of coal as an energy source, the coal dust explosion in mines, especially in mines, caught the attention of the scientific community. And then in the second half of the 20th century, dust explosions were reproduced on a lab scale to be studied and classified. Nowadays, we can associate to dust explosions fast combustion processes involving finely dispersed material, finely subdivided material. We can count on detailed and deep experience feedback, represented also by some incident reports. For example, in the combustible dust incident report on the 2020 edition, we can find some important information, some essential information to understand these phenomena, such as the type of the powder involved in dust explosion phenomena. Here, for example, you can notice how food products and wood products represent the majority of the dust explosion incident. And this is one of the main reasons why this thesis was focused on the study of the organic dust explosions. In order to understand and comprehend the complexity behind dust explosion, we can, for example, look at the so-called hexagon of dust explosions. The hexagon of dust explosion resembles the 6 conditions fundamental to be in the presence of a dust explosion. First of all, we always need an ignition source, an oxidizer, and a fuel, combustible material, here represented by fine powders. But then we need a dispersion step. We need a certain concentration associated to the dust cloud that lays in the explosibility region, and a certain confinement level to be in the presence of the overpressure effect characteristic of an explosion. Although these conditions may represent well the complexity of a dust explosion, to fully understand them, we need to look at the fundamental phenomena involved in the global one. So we can, for example, let's start considering dust deposits, so a powder in a quiescent and static state that we disperse in the form of a dust cloud. We can call this process the dispersion step. Eventually, the dust cloud on its path can encounter an ignition source that can locally increase the temperature of the particles. So we are talking about the particle heating step. If the increase of temperature is high enough, the pyrolysis reaction may be triggered and pyrolysis product can be generated in the gaseous atmosphere around the particles. Eventually, in the presence of an oxidizer, a flammable atmosphere can be created and oxidation reactions can be triggered. The exothermicity associated to these reactions lead to a heat wave propagation within the dust cloud and important relative heat transfers. If we zoom in, we can always characterize this step with three zones: the preheating zone, the reaction zone, and the post-reaction zone. If we zoom out, we can identify a step known as the flame propagation step. So the propagation of the heat wave and the flame front in the dust, within the dust cloud leads to the flame propagation that eventually leads to an overpressure wave. This complexity can be resumed in 6 fundamental steps. So I presented you the dispersion step, the first one, then a particle heating step, then pyrolysis and oxidation steps that leads to a flame propagation within the dust cloud, and finally the overpressure wave. This is also the global approach of this thesis. So we took the global phenomenon of an organic dust explosion, we split it in 6 different steps, and we wanted to create and propose an experimental tools, eventually supported by modeling, to analyze and to characterize qualitatively and quantitatively each step. First section, so the first section of the results will be focused on the dispersion step. The second one will be more focused on the particle heating and the pyrolysis steps in a dust cloud. Third one will analyze the pyrolysis and oxidation reactions and their role in an explosion. So we will be considering also the overpressure wave results. And finally, I will be presenting you some results concerning the flame propagation and including also some overpressure wave results. So let's start with the section, with the outline. I presented you with the 4 sections, and general conclusions and perspective for the future will be also presented. Then let's start with the first one, the first section, focused on the dispersion step. First of all, we wanted to develop an experimental strategy for this section. We asked ourselves what we need for, and we found 5 main answers. First one, we needed to control the dispersion conditions in order to study them and their influence on the final results. Then we wanted to use a lab scale setup to develop a non-intrusive approach to study some characteristics of the in situ characteristics of the dust cloud. And then we added also the possibility to set the temperature of the setup. The choice fell on the Gobbe-Greenwald furnace. It's a standardized apparatus usually used for the determination of the minimum ignition temperature of a dust, and we adapted it to our needs. The main characteristic that we wanted to study was the dust cloud PSD, so the particle size distribution. We took the GG furnace, the Gobbe-Greenwald furnace, and we developed an experimental method to study the time and space evolution of the dust cloud PSD in this apparatus. So it is normally formed by 3 main parts: gas pulse generation system to the left. The horizontal one to the top is the dust cloud generation system. So the powder is dispersed and passed through the final part, vertical chamber. In order to study the space evolution, we selected position 1 to perform the analysis of the PSD, so just after dispersion. Position 2, just after the main obstacle on the path of the dust cloud. And position 3, the exit of the vertical chamber. Concerning the PSD measurement, we took the GG furnace, we placed it in between the 2 elements of a laser diffraction sensor, and we were able to collect the PSD curves each 10 milliseconds. So it was a high frequency acquisition analysis, and we used this analytical tool to characterize the dust cloud PSD for the over time and for the free positions. Concerning the choice of the powder, so the organic dust that we selected, we've chosen 7 powders plus a reference powder. We characterize them in terms of naked eye appearance, in terms of optical microscope imaging, so to characterize the particle shape of the particle shape. And with the scanning electronic microscope, we characterize both the shape of the particles and the morphology of the surface. We've chosen 4 different celluloses to study the influence of the initial PSD on the dispersion step. Then with starch to study a molecule that has the main monomer as cellulose but different chain structure, so different properties of the material. We selected glucose and ascorbic acid to introduce some completely different chemical nature between among the powders, and glass beads as reference sample. The first layer of information, the first series of experimental results is represented by the residence time of dust cloud in the GG furnace. So we placed a high-speed camera in front of the GG furnace, and we created a visualization window in position 1 in order to follow the dust cloud passing in position 1 and position 3. We were able to determine the mean residence time of the dust cloud as a function of the dispersion pressure and as a function of the injected masses. If you look at the graph to the right, we can identify 2 regions. One to the left, an decreasing trend, and one to the right, so a decreasing trend. The decreasing trend was expected as we are increasing the dispersion pressure, so we are increasing the gas velocity and then the velocity of the dust cloud. The first one, so the increasing trend, was not expected, and it can be related to a highly important efficiency of dispersion. So we are dispersing more and more powder in the setup. The second layer of information is represented by the agglomeration index. So we wanted to quantify the agglomeration tendency of each powder. We plot the D90, a characteristic diameter, as a function of the time. As you can see, for example, if we consider position 1 and position 3, we can notice a high agglomeration tendency, which we wanted to characterize, to quantify. So we calculated the normalized difference between position 3 and position 1, and we calculated the agglomeration index here, for example, associated to D90, but also associated to D10 and D50. As you can see, we can identify 2 different classes. The first one is associated to high agglomeration indexes. The second one to lower agglomeration indexes. Abyssal pH 105 and mid starch are the finest samples, so we can associate fine particle size to high agglomeration indexes. Abyssal pH, the 3 on the right, are the coarsest samples. But we cannot associate coarser particles to low agglomeration indexes because, for example, glucose represents the coarsest sample among the others. So we wanted to study the influence of other parameters on the agglomeration tendency. We simply sieved each sample to obtain 5 different fractions, and we dispersed them in a similar way as the sample as they are. We obtained a peculiar behavior for all the celluloses, so we can notice a decreasing tendency to agglomeration as the mean initial D10, so the final fraction, increases. But at the same time, for starch and glucose, we didn't observe any peculiar agglomeration tendency. So we can, and they are similar, comparable. We can introduce also the characteristic, the influence of the chemical nature of the 2 samples in the agglomeration tendency. In order to conclude this first part, if we consider a dispersion step, we can always have to take into account the heterogeneity associated to a dust cloud. There are finer and coarser particles that leads to different agglomeration phenomena. The finest fraction is more prone to surface weak bonds interaction. The coarser particles are more prone to entanglement, so geometrically interaction between the particles. A high level of segregation that modifies the residence time distribution of the dust cloud. The duality between the residence time and the shear stresses, which is influenced by the dispersion pressure. And then a final important influence on the ignition phenomena at higher temperature. This leads us to the second section, so more focused on the behavior of dust cloud in terms of particle heating and pyrolysis. We consider the same experimental setup, but we slightly modified it. We added a section, like a final section, in order to be able to create an inert atmosphere inside the setup, and at the same time, we wanted to be able to collect solid products, the condensable fraction, and the gaseous products coming from the flash pyrolysis in the dust cloud. The experimental procedure was consisted in dispersing 0.2 grams of cellulose here, but we performed other tests on other powders in the GG furnace at different temperature, and characterization of the different fractions of pyrolysis and combustion tests with different analytical techniques. In order to create the first layer of information, we wanted to add some information about the particle temperature profile. We considered the dust cloud passing through the cylindrical chamber, and we considered the three main heat transfer modes to non-spherical particle of cellulose. We consider the radiation, we consider the convection in the gaseous phase, sorry, and the reaction, the heat associated to the different reactions. We elaborated the model. We consider the particle temperature and the particle thickness as the two variables, and we were able to combine these results to experimental data to elaborate what we call the dust cloud thermal analysis. The first layer of information comes from the optical concentration. So from the previous study, we were able to characterize something related to the resonance time distribution of the dust cloud over time. We considered the optical concentration in position 1 and 3, so respectively before and after the heated chamber. And we added the mean dust cloud residence time determined with the high-speed camera approach, and the results of the particle temperature profile, here represented by the diameter of the particle as a function of the time. We associated the evolution of the diameter to a conversion degree of the particles. As you can notice, for finer particles, the conversion is almost equal to 1. For more coarser particles, especially the 200 microns ones, you can notice a non-complete conversion. We can just notice a heating of the particles. This was confirmed by the analysis of the solid products. The images obtained with the optical microscope allowed us to stress out the heterogeneity of the degree of the conversion degree. Here you can see an increasingly converted residue as the temperature increases. The scanning electronic microscope allowed us to confirm these results, especially in terms of surface morphology. We can notice an increasingly important volatilization and agglomeration of the particles. And to support these results, we performed infrared absorbance. We were able to isolate these molecules, some characteristic molecules. For example, the OH stretching band is associated to a higher important accessibility to the monomer of the cellulose, and this is confirmed by the two bands to the right, the monosaccharide, the bands related to monosaccharides in general, so associated to the monomer of the cellulose. As for the condensable products, we were able to isolate one key molecule, the levoglucosan, representing the main product of the flash primary pyrolysis. It is also in our test, it is also related to cracking reaction, and oxidation reactions. With the GMS, we were able to stress out an increasing production of levoglucosan as the temperature of the reactor goes from 700 to 800 Celsius, and a subsequent cracking of levoglucosan as the temperature increases to 900. With the combustion tests, we were able to stress out the consumption of this molecule in the oxidation reactions. Finally, as for the gaseous products, we isolated H2, hydrogen, methane, CO, and CO2 as most abundant products. We can notice a high influence of the temperature of the reactor for the methane. And if we compare these results with the combustion tests, we can notice a very slight influence of the reactor temperature if we consider the hydrogen. Methane represents the it's importantly converted in the oxidation reactions. CO, which can be associated to a semi-complete reaction of oxidation, is way higher, way more abundant in the combustion tests. CO2 is slightly higher in the combustion test, but still comparable to the pyrolysis ones. All these results were introduced in a MATLAB fitting code in order to elaborate a fast mechanism of pyrolysis conceived with operating conditions characteristic of dust explosions. So we were able to elaborate these mechanisms consisting in 5 reactions. The first one is the activation of the cellulose, which leads to the production of the tar, here represented by the levoglucosan, which in turn converts into gaseous products. The third one is represented by the direct conversion of the cellulose into gaseous products. And the last one is the conversion of cellulose into char and water. We were able to determine the activation energy and the pre-exponential factor for each for reaction 3, 2, and 4. And we were able to characterize the fast cellulose pyrolysis reactions in the condition of a dust explosion. This leads to some important conclusions. If a dust cloud is subjected to a heat source, we can always characterize we can always identify a particle heating step, which can be the rate limiting step if the particle size is high enough. Then primary pyrolysis, here represented by the volatilization of the finer particles and at the same time the polymerization of the solid phase of the cellulose. Then a secondary pyrolysis reactions, represented here mainly by the cracking of levoglucosan. And then the heterogeneity characteristic of a dust cloud leads to some agglomeration involving also tar molecules. And finally, the oxidation reactions involves levoglucosan consumption and incomplete combustion verified with the gaseous products analysis. The third section is represented by the study of the role of pyrolysis and oxidation reactions by considering them as a part of an organic dust explosion phenomenon. The experimental strategy was elaborated considering the different phases involved in a dust explosion phenomenon. So we can always encounter unreacted particles, vapor phase, represented by water or tar molecules, pyrolyzed particles, gaseous phase, and ashes. So we wanted to represent each phase with a different compound. We selected, for example, pure cellulose to represent the unreacted particles. We selected different tar-coated celluloses to represent the vapor phase. So we just took pure cellulose and we introduced some tar from flash pyrolysis of cellulose. We mixed it up, and we obtained 4 different powder associated to 4 different concentration of tars. The gaseous phase. As for the gaseous phase, we considered the results from the previous study from section 2, and we elaborated 2 gaseous mixtures, mix A and mix B, to evaluate the influence of the temperature of the reactor with the explosion tests. In the explosion tests, the pyrolyzed particles and the ashes were merged together and were represented by biomass char. The experimental procedure consisted in using the 20-liter sphere, a standardized vessel used to determine the explosion severity parameters of a dust explosion. We can always obtain a curve like this, so we can plot as a function of the dust concentration the explosion overpressure and the rate of pressure rise, in order to identify Pmax, so the maximum pressure attained over a series of tests, and the dPdt max, so the maximum rate of pressure rise obtained over the series of tests. We performed these tests with pure cellulose and the 2 pure gaseous mixtures. We obtained, as for considering the rate of pressure rise, some very different results. For example, for cellulose, as you can see, we can attain approximately 250 bars per second, while for mix A and mix B, we respectively attain almost 1,000 and almost 2,000 bars per second. This is due to the different composition of the 3 compounds, especially considering the mix A and mix B, especially the hydrogen fraction of the 2 gaseous mixtures. Then we perform some hybrid mixture tests. So a hybrid mixture is a mixture composed of at least 2 different fuel combustible phase, here represented by pure cellulose and one of the 2 gaseous mixture. We firstly approach these tests by keeping the initial mass of the system constant. So we introduced, for example, 10 grams of cellulose. We evaluated the explosion severity parameters for this test, and then we subsequently substituted a certain amount of cellulose with the same amount of gaseous mixtures. As you can see, we can, for example, identify a slight variation of the PM. So by keeping the mass constant, the mass of the system constant, we are also keeping the energy release constant. So in terms of PM, in terms of maximum explosion over pressure, we cannot notice any important variation. We can, on the other hand, notice a minimum point of the dPdTm corresponding to high concentration of mass of cellulose, an increasingly accelerated kinetic as we substitute the powder with the gas mixture, and 2 different maxima corresponding to small amount of powders. So we can conclude that by introducing small amount of powders in a gaseous explosion, we can slightly increase the dPdTm, which can be related to the increased enhanced relative heat transfer between the reaction zone and the preheating zone. The second approach consisted in keeping the equivalence ratio constant. So here you can see the dust concentration as a function of the gas concentration. We can notice, as for the dPdTm, a region associated to high explosion severity, and at the same time to high variability. We can notice also the important effect of the equivalence ratio on the dPBTM, and we can identify around 30% of gas concentration approximately, maximum point for dPBTM. These results leads to some important conclusions when considering the dust explosion phenomena. We always, it's very important, it is mandatory to consider the role of the radiative heat transfers in the global phenomenon. The flame propagation can be increased by adding a small amount of powder in the phase, in the exploding phase, in the exploding system. And each organic dust explosion can be associated to a certain hybrid mixture system. The last part consisted in studying the flame propagation step. So we introduced also some results relative to the explosion of pressure. The approach was simple. We wanted to compare different results from different experimental setups. The first two setups are represented by open 20-liter sphere. So it's the standard 20-liter sphere equipped with a relief valve and a visualization window that allows us to follow the propagation of the flame kernel in the dust cloud, within the dust cloud. The second one is consisted in a vertical flame propagation tube equipped with a dispersion system, 2 electrodes that ensure the presence of an ignition source, here represented by an electrical spark, and a relief valve for the exit of the combustion products. This can be associated to high-speed videos, so we can exploit the high-speed videos of these two setups in order to evaluate the flame propagation within the dust cloud. So these two setups allowed us to access to some information, some global information about the propagation step within the dust cloud. And then we wanted to add some more information. We elaborated a microfluidic bed burner, which consisted in three main parts. We have a microfluidic bed, so a fluidized sand bed, and then a feeding system at the top in the image, and then a nozzle burner. So by placing a high-speed camera in front of the nozzle burner, we were able to record high-speed videos of the flame and then evaluate the flame speed of the gaseous products. So the concept, the idea behind this approach was to separate the pyrolysis step, the oxidative pyrolysis step occurring in the sand bed from the oxidation, which occurs in the homogeneous phase in the flame. First of all, we needed to characterize the microfluidic bed. We placed the same high-speed camera in front of the setup. We were able to visualize the sand bed the fluidized sand bed through a visualization window in the reactor, and we were able to record this kind of videos. The videos of the fluidization contains a lot of information. We selected some important, the principal ones are represented by the sand bed height and the frequency of bubbling of the splash zone, then the bubble size, the sand bed color, and the char content that can be associated to a certain color of the sand bed, the fluidization movement of the sand bed, and then finally the gas preferential path. We selected the first two, and I will be presenting you the results concerning the sand bed height. The videos were decoupled in 100 frames, which constituted the input image in a MATLAB code. We were able to calculate the relative bed height of the microfluidic bed as a function of the ratio U to UMF, so the minimal fluidization velocity. We were able to characterize the expansion of the bed due to an increasingly high U to UMF ratio and the effect of the temperature. This allowed us to select the optimal operating conditions in order to produce a stable flow of pyrolysis products with a stable fluidization. So we were able to, by changing the different parameters, we were able to select the operating conditions in order to obtain a stable fluidization. As you can see here at 400 degrees, both with nitrogen and air, the fluidization is homogeneous, is stable. The regime of fluidization is constant, and we can associate. We can once that we are sure that we are able to control the fluidization, we were able to generate a rather stable flow of gaseous product, of pyrolysis gaseous products. In terms of flame propagation speed, we started with the vertical tube. We were able to follow the propagation of the flame kernel. Then, for each frame, we extrapolated the contour of the flame. We were able to plot the flame speed as a function of the Karlovic's factor, which allowed to quantify the stretching of the flame. By considering the linear trend here represented by the blue dotted line, we can isolate the flame speed associated to a Karlovic's factor of 0 and then to an unstretched flame speed. So 22 centimeters per second, it represents the unstretched flame speed. So the flame speed, the speed of the flame propagating in the dust cloud. Second results concerning the 20-liter sphere, we wanted to introduce a different approach from an experimental one. We considered a semi-empirical relationship that allows to connect the explosion overpressure results, the explosion severity results, to the dust concentration, the series-linear relationship. We were able to calculate the unstretched flame speed as a function of the dust concentration, and by isolating the range associated to an equivalence ratio of 1, we were able to determine a range of unstretched flame speed between 20 and 23 centimeters per second. This was compared to a more experimental approach. So with the open 20-liter sphere, the approach is the same as with the vertical flame propagation tube, and the flame speed, the unstretched flame speed determined here was 26.6 centimeters per second. These results come from Santander et al., who was working with nanocellulose. So the little discrepancy of the two values presented so far can be due to a different particle size of the dust cloud. And then finally, the microfluidized bed burner, we were able to stabilize a flame. We were able to calculate then the alpha angle and the flow, the gaseous flow needed to determine the flame, the laminar flame speed of the hot gases. We consider the little cone flame, and we calculated an alpha angle for each frame, which leads to a flame speed, a laminar flame speed as a function of the time. By considering the region where we were able to stabilize the flame, we were able to determine a laminar flame velocity of approximately 140 centimeters per second relative to the hot gases. This leads us to important conclusions concerning the flame propagation step. First of all, heterogeneity and turbulence are characteristics of the dust cloud. So we were able to carve out the turbulence and the heterogeneity, the characteristic of a dust cloud, by introducing the experimental approach of the microfluidized bed. Then the flame propagation and the flame speed in general allowed us to compare different phenomena. And we were able to validate the feasibility of this experimental approach. of determining the flame speed. General conclusions and perspective for the future. We were able to characterize the dust cloud in terms of PSD. We were able to characterize the particle heating step and the pyrolysis step in the dust cloud. We used the 20-liter sphere to perform some hybrid tests and to perform some explosion severity tests as well. The flame propagation results in the 20-liter sphere were compared to other two experimental setups. The microfluidic bed was characterized in terms of fluidization, and the flame speed of the pyrolysis gases products was determined. In the flame propagation too, the unstretched flame speed was determined and compared to the other two setups. We can conclude in general that the PSD, the particle size distribution of a powder, strongly influence the behavior of the dust cloud and has a primary role on the determination of the rate limiting step of the global phenomenon. For larger particles, we can associate the rate limiting step to the particle heating step, while in most cases for finer particles, the pyrolysis step is the rate limiting one. We were able to stress out the influence of the gases products composition in terms of influence on the global phenomenon, especially the composition H2 fraction. Pyrolysis mechanism was proposed and validated, and the oxidative pyrolysis and the homogeneous combustion of the products were decoupled, and flame speed was used to compare different results. In terms of perspective for the future, we were able to create a flame from oak wood. So we substituted the cellulose with oak wood, but we were not able to stabilize the flame high enough to perform some high-speed video analysis. And then we would like to couple our results in terms of kinetic mechanisms with some CFT already present in the literature to pass from a CFT, a pure CFT, to reactive CFT, and why not elaborate an organic dust explosion predictive model to determine the explosion severity parameters and the flame speed values. I would like to thank everyone that stepped in my path. In these 3 years were very difficult, very easy to, very difficult, but I'm very happy with the results. I'm very happy to be in the presence of some amazing people. I would like to thank the jury, the member of the jury to be here, and my pre-supervisor for guiding me through this difficult and complex path. And grazie a tutti, alla mia famiglia, ai miei amici che mi hanno sostenuto sempre in questi anni. Thank you.
Okay. Thanks a lot for this very nice, excellent presentation. Very clear, technique, but and second. Okay. And we will start question again. All the members of the jury. And we are going to start with one of your for the manuscript.
Okay, so I have the pleasure to start with torture. This will never be a torture, I think. Indeed, first, I would like to congratulate you for this impressive work you've done. In both quantity of work, but also and chiefly in the quality of the work you developed, in the smartness of the research strategy you developed. I think it was a really smart strategy, making use of quite conventional equipment in a very unusual way of operating them to extract this impressive plots, sets of results that you got from a detailed characterization of the role, for instance, of PSV in the dynamics of the cloud environments, in the way we go from the inert dust cloud formation up to the flame propagation and development of the pressure wave coming out and terminating the phenomena. I think that you accessed and achieved significant innovating results in the field, and it was not so obvious to go to such targets because, as you know, through the literature review, you clearly explained that we have worked on the matter for decades, if not centuries. But we are still, you proved that we are still a lot of learning in the matter, in particular once you address very complex stuff like organic matters, in particular those that you studied as examples. So really, again, congratulations.
Thank you.
That's the first thing I wanted to stress. Secondly, as already expressed by the president of the jury, the presentation was quite clear. Lots of things to present in a very short time, of course, but it was presented quite clearly with lots of illustrations that were greatly helpful to fully follow your presentation. Having said that, I would like to come back to the manuscript at first. As I said already, once you looked through this manuscript, I must confess I had some difficulties at the beginning because of the structure of this document, which is a compilation of projects of publications on which you do not know exactly the status so far. I was a little troubled because you started by giving one page with the publication list, which is in fact is not the publication list, but only those that you did not use to develop your manuscript. So I understood this afterwards. I was also a little bit disturbed by the fact there were plenty of abstracts, general one in French and English, and then other ones coming on. And it took me some time to understand that those other abstracts were synthesis from the following chapters. At the end, I was finding these short abstract quite helpful to follow, but it was not so evident at the beginning to understand the strategy you follow to develop your manuscript. But indeed, at the end, it was not so difficult to follow. Okay, you developed a very nice first chapter that confirmed that you had a very detailed look in the literature to understand what was done previously, and it has certainly clearly oriented your strategy that you developed in the explanatory part and the modeling part. So it was even for me quite informative, although I'm already quite learned on dust explosion and gas explosions, of course, according to my profile. But I learned a lot on that, and I would like to give you one advice. This chapter would also deserve a kind of review publication. Just have to find the perspective in which, yes, but the advice I would give you with the, let's say, would be a review paper on what we know about dust explosions once organic materials is. But my advice would to provide that kind of review paper, not within the safety science community, but maybe in the biomass community that do not know anything about safety. For instance, addressing this in biotechnology journal or things like that would be very useful, I think. Okay, I have a number of small questions. We already talked about the structure, which in my view was quite pertinent. Of course, I have to stress the impressive varization activity already achieved and certainly ongoing. It was most of the chapters are already manuscript. I discussed a little bit with Olivier to know about what's the status, but if you're doing some update of this document, I would advise you to make an update of the publication, because somebody that would use your manuscript at later stage would like to know where these documents have been published at the end.
Yeah, I will add something in the
minor modification of the manuscript that would be very helpful for the next one. That
sure.
Take the lead of the perspectives that you have mentioned in your oral presentation. Of course, the manuscript is written in English, in very good English, very easy to read. Practically no corrections to make as regard the quality of the language used, of course. I was just a little bit disappointed with the quality of the general conclusion. From my point of view, you did not distinguish enough what has been done from the perspective. Kind of mixing that in that chapter that might be done better.
And perspectives. Yeah,
this is just a minor. This is my point of view. Maybe it's not the one of the other members of the jury. I have a number of small questions by now. If you go to chapter 1 in the bibliographical review, what would you guess in terms of minor differences if you have to compare dust explosion phenomena with organic stuff that you studied in your work as compared to other types of material that can undergo dust explosions, like, for instance, sulfur or metallic powders? What major types of phenomenologies would you suspect that would differentiate these different types of dust explosion?
I think the main difference would be the reactions involved, especially the reaction of pyrolysis involved when dealing with organic dust, especially when we are talking about biomass or complex dust. For example, with some metallic dust or sulfur dust or coal dust. Even coal dust is rather simple than the pyrolysis reaction and the oxidation reactions involved with this kind of material.
What would you suspect, for instance, about minimum energy level?
In terms of minimum
sulfur, for instance.
Lower than biomass.
It's very low for sulfur. It's one big issue with sulfur. It's really low.
So the composition.
Very close to gas. Gas explosion has it.
It's the same thing for coal, for example. We tested some coal dust. We noticed that the MIT was really lower.
Elementary as well. But,
so for biomass, the main issue is the presence of some recalcitrancy. Thermal recalcitrancy of, for example, lignin and hemicelluloses. So the MIT or the ignition sensitivity is very lower than, for example, sulfur or coal dust. So the reaction.
Very good. Good answer. I saw also that you looked into the accidentology, which has been reported by many researchers, and I saw that you exploited essentially databases of American origin, in which we have very little information about what is the situation in France. Have you an idea if the accidentology in France is quite presenting the same trends as the general trends that is coming out of your analysis of the accidentology, or do you suspect something different?
So when I
had a look in the LRGP database, for instance, which is more focusing on the French side. It would have been useful also to check whether we have more or less statistically the same situation in terms of sectors that are affected by this explosion. Because there are so few examples in the American database about what has been disputes in the matter in concept.
So when I was compiling the accidentology, the table with all the incidents related to this explosion, I noticed a difference between Europe, America, and Asia, for example, which is, I think, due to the different primary matters, primary source of energy.